Good morning, everyone. My name is Muskan, and I am here to explain the chapter Electrochemistry. In this, the chapter is divided into three sections. First section is electrolytic conductance and its measurement. Now, our first topic is electrical transport. A substance which allows an electric current to pass through it is called a conductor, while the substance which does not allow electric current to pass through it is called an insulator or non-conductors. The conductors are of two types via electronic conductors and electrolytic conductors. First is electronic conductors. Electronic conductors are the substances which do not undergo any chemical change as the electric current flows through them. For example, metals, graphite, and some minerals. The conduction through electronic conductors is due to the flow of electrons in them. Second is electrolytic conductors. They are the substances which conduct electricity in their molten state or through their aqueous solution and which are decomposed by the passage of electric current. For example, aqueous solution of acids, bases, and salts, molten states. In this type of conductors, the electric current is due to the movement of by ions. This type of conduction is referred to as electrolytic conduction. Electrolytes are further classified as strong electrolytes and weak electrolytes. Strong electrolytes are substances which are almost completely dissociated into ions in their aqueous solutions or in the molten state. For example, strong acids like HCl, H2SO4, etc., strong bases like NaOH, KOH, etc., and salts like NaCl, NH4Cl, etc. Weak electrolytes are the substances which dissociate in aqueous solution to a smaller extent. In other words, they have low degree of dissociation. For example, weak acids like HCN, H3PO4, CH3, COOH, and weak bases like NH4OH, etc. Since they have low degree of dissociation, so they conduct electricity to a small extent. Non-electrolytes, substances like urea, glucose, etc., which do not conduct electricity in molten state or through their aqueous solutions, are called non-electrolytes. Ethyl alcohol, sugar are also examples of non-electrolytes. It is interesting to note that whereas the electrical conduction of electronic conductors decreases with increases of temperature, but in case of electrolytic conductors it increases with temperature. Next is factors affecting electrolytic conduction. In aqueous solution or in molten state, the electrolytes split up into ions. The free movement of ions is responsible for the conduction of electricity. The electrical conductivity of the solution should therefore be related to the number of ions present in the solution. Some of factors on which electrical conductivity of the solutions of electrolytes depends are: first, the interionic attraction. These are the attractive interactions between the ions formed by the electrolytes in solution and are commonly known as solute-solute interaction. Larger the interionic attraction, lesser is the freedom of movement of ions and smaller will be electrical conductivity. Second, the solvation of ions. These are the attractive interactions between the ions of the electrolyte and molecules of the solvent and commonly known as solute-solvent interaction. Larger the solute-solvent interaction, larger will be the solvation, lesser will be the movement of ions, and hence lower will be the electrical conductivity. Third is viscosity of the solvent. This factor depends upon the attractive interaction between the solvent molecules, which is referred to as solvent-solvent interaction. Larger the solvent interaction, larger will be the viscosity and more will be the hindrance to the movement of ions. Hence, lower will be the electrical conductivity. The above factor decreases with increase in temperature. As a result, the kinetic energy of the ions increase or decrease in temperature. This results in the increase of electrical conductance of electrolytic solution with rise in temperature. This is in contrast to the behavior of electronic conductors in which the conductance decreases with increase in temperature. Alternatively, we can say that the conductivity of electrolytic solutions depends upon the following factors. First is nature of the electrolyte. The conductance of an electrolyte depends upon the number of ions present in the solution. The number of ions produced by an electrolyte depends upon its nature. The strong electrolyte dissociates almost completely into ions in solution, and therefore the solutions have high conductance, whereas weak electrolytes dissociate to only small extent, hence their solution have low conductance. Second, nature of the solvent. Electrolytes ionized to greater extent in polar solvent. Therefore, greater the polarity of the solvent, larger is the ionization and hence greater is the conductance. Third, concentration of the solution. On increasing the concentration of electrolytic conductance decreases in case of both weak as well as strong electrolytes, because with increase in concentration in case of weak electrolytes the ionization decreases, and in case of strong electrolyte the interionic attraction increases. Fourth factor is temperature. The conductivity of an electrolyte depends upon the temperature. With increase in temperature, the conductivity of an electrolyte increases due to increase in dissociation. Now, there is a difference between metallic conductors and electrolytic conductors. First is metallic conductors. These remains unchanged as the current flow through them. In electrolytic conductors, they undergo a chemical change by the passage of electric current. Second, flow of electricity is due to the presence of mobile valence electrons, so it involves no transfer of matter. In electrolytic conductors, conduction is carried by ions, hence it involves transfer of matter as ions. Now third point in metallic conductor is metallic conduction involves no change in the properties of the conductor, while electrolytic conductions involves the decomposition of the electrolyte as a result of chemical reaction. The resistance in metallic conductors is due to the vibration of metal ions about their mean position, which hinder the flow of electric current, while in electrolytic conductors, the resistance of an electrolyte solution is due to the factors like interionic attraction, viscosity of the solvents, etc. Fifth point is metallic conduction decreases with increase in the temperature. This is because on increasing temperature, the frequency of the vibrating kernels increases. Consequently, the resistance of metallic conductors increases, which creates hindrance to the flow of electrons and its conductance decreases. While in electrolytic conduction, the electrolytic conduction increases with temperature. This is due to the increase in the dissociation of electrolyte and decrease in interionic attraction with increase in temperature. The conductivity of metal is generally high, and the conductivity of electrolytic solution is generally low. Next is electrical resistance and the conductance. Electrolyte solutions conduct electricity through them by the movement of ions towards the electrodes. Like metallic conductors, electrolytic conductors also offer resistance to the flow of electricity. Hence, electrolytes also obey Ohm's law. According to Ohm's law, the current I flowing through a metallic conductor is directly proportional to the potential difference across. That is, I is directly proportional to V. I is equals to VR, V divided by R. Now V is equals to IR, where R is the constant of proportionality and it is known as resistance of the conductor. It is expressed in ohms and it is represented by ohm. Current is generally measured in amperes and potential difference V is measured in volt. According to Ohm's law, the unit of resistance is ohm. In terms of SI base unit, ohm is equals to kilogram meter square per centimeter ampere square. The unit is obtained as per the formula is given. The interesting feature of an electrolytic solution is not the resistance they offer to the flow of electricity, but what they allow it to flow. Consequently, the important property in electrochemistry is conductance. Thus, conductance is measure of case with which current flows through a conductor. From Ohm's law, it follows that a substance which which offers lesser resistance, will allow more electricity to pass it. Thus, conductance is the reciprocal of resistance and it is represented by C. That means C is equals to 1 by R. And the unit of conductance are reciprocal ohm, that is ohm inverse or mho. Ohm is abbreviated as del and the ohm inverse may be represented as ohm. Electrical conductance is also expressed as Siemens. 1 Simon is equals to 1 ohm inverse, named after noted electrical engineer Sir William Simmons. Specific conductance. Now next is specific conductance, equivalent conductance and the molar conductance. First we will do specific conductance. The resistance R of a conductor is directly proportional to its length and inversely proportional to its area of cross section, where rho is a constant of proportionality and it is known as specific resistance or resistivity. The value of rho depends upon the nature of the material of the conductor. Thus, the specific resistance or resistivity rho is defined as the resistance of a conductor of 1 centimeter length and having area of cross section equal to 1 centimeter square. In other words, resistivity or specific resistance is the resistance between opposite faces of 1 centimeter cube of the conductors. In SI unit, it is defined as the resistance when the conductor is 1 meter long and its area of cross section is 1 meter square. That is resistance of 1 meter cube of the conductor. Units of resistivity are ohm centimeter. The reciprocal of specific resistivity rho is known as specific conductance. It is denoted by symbol K and it is pronounced as kappa. Thus, K is equals to C into L by A. If length is equals to 1 centimeter, area is 1 square centimeter, then kappa is equals to the conductance. Hence, specific conductance is defined as the conductance of a solution of 1 centimeter length and having 1 square centimeter as the area of cross section. In other words, specific conductance is the conductance of 1 centimeter cube of the solution of an electrolyte. The units of specific conductance are ohm inverse, centimeter inverse, or we can also say Simon centimeter inverse. Now next is equivalent conductance. The current in an electrolyte is carried by ions. A particular volume of solution may contain more or less ions depending upon its nature. Therefore, the conductance of a solution varies with the concentration. So for comparing the conductance of different solution, it is required that they should have the same volumes and must furnish amount of ions carrying same total charge. This can be achieved by taking equal volumes of the solution containing their respective gram equivalent masses. The conductance of such solutions is called gram equivalent conductance. Equivalent conductance may be defined as the conductance of a solution containing 1 gram equivalent of the electrolyte dissolves in V centimeter cube of a solution such that the whole of the solution is placed between two electrodes 1 centimeter apart. This is denoted by a simple lambda q eq. Equivalent conductance represent the conducting power of one equivalent of the given electrolyte at the given dilution or concentration at the temperature. Next is relation between specific conductance and equivalent conductance. The equivalent conductance lambda is equal to the product of the specific conductance and the volume V in centimeter cube, which contains 1 gram equivalent the electrolyte does. Lambda EQ is equals to K into V. The relationship is deduced as follows. Consider a rectangular vessel with its opposite walls acting as electrode placed at distance of 1 centimeter. Suppose 1 centimeter of the solution containing 1 gram equivalent of electrolyte is placed in this vessel and its conductance is noted. The conductance of this solution represents specific conductance K. Further, as 1 centimeter cube of the solution contains 1 gram equivalent of the electrolyte, hence its conductance will be its equivalent conductance. Thus, for 1 centimeter cube of the solution containing 1 gram equivalent of electrolyte, the equivalent conductance lambda EQ is equal to its specific conductivity. Now consider 4 centimeter cube of the solution containing 1 gram equivalent of electrolyte placed between two electrodes 1 centimeter apart. The solution can be considered as consisting of 4 cubes, each of volume 1 centimeter cube. The conductance of each of these cubes is equal to the specific conductance K. Thus, the total conductance of the solution will be 4K. Similarly, VCC of solution will contain V cubes and the total conductance will be K into V. Electrical conductance is equals to specific conductivity N to V. In terms of concentration, if a solution contains C gram equivalent of electrolyte in 100 cc in 1000 cc of the solution, then the volume of the solution containing 1 gram equivalent will be 1000 divided by C. Thus expression 1 can be written as del lambda eq is equals to K into 1000 by normality. Units of equivalent conductivities are ohm inverse centimeter square equivalent inverse or Simon centimeter square equivalent inverse. Now this is molar conductance. Molar conductance of a solution at dilution V is defined as the conductance of all the ions produced from 1 mole of the electrolyte dissolves in V centimeter cube of the solution such that the whole of the solution is placed between two parallel electrodes 1 centimeter apart. It is denoted by lambda m. Now, there is a relationship between molar conductance and the specific conductance. Molar conductance of solution is obtained by multiplying the specific conductance by volume in V centimeter cube, which contains 1 mole of the electrolyte. Thus, lambda m is equals to K into V, where V is the volume of the solution in 1 centimeter cube containing 1 gram mole of the electrolyte. If a solution contains a C mole of electrolytes in 1000 centimeter cube of the solution, then the volume of the solution containing 1 mole will be 1000 divided by C. The above expression can be written as lambda m is equals to K into 1000 by molarity. Here K is the specific conductivity and C is the molar concentration, that is mole per liter. So the units of the molar conductance are ohm inverse centimeter square mole inverse. Now we will do measurement of conductance, specific conductance and equivalent conductance and molar conductance. First we will do measurement of conductance. The conductance of a solution is reciprocal of the resistance. Therefore, it can be determined by the measurement of resistance of a solution. The resistance of solution can be measured with the help of Wheatstone-Bridge method. The principle of Wheatstone-Bridge method is as follows. It consists of 4 resistance R1, R2, R3 and R4. If resistance R1 is variable resistance and R2 is unknown resistance of the electrolyte solution. When the current flows through the circuit, the resistance R1, R2 and R3 are so adjusted that a null point is obtained. The null point is indicated by zero deflection in the galvanometer at G. Then add null point R1 divided by R2 is equals to R3 divided by R4. The resistance R1, R3 and R4 are known and the value of R2 can be calculated. To determine the resistance of the electrolyte solution, one arm of Wheatstone bridge is attached to the conductivity cell containing the solution. The conductivity cell is made up of Pyrex glass and it is fitted with platinum electrodes. These are coated black with finely divided platinum. However, for measuring the resistance of an electrolyte solution, direct current cannot be used because it causes electrolysis of the solution. As a result, the concentration of electrolyte near the electrode changes and this results in the change in the resistance of the solution. These effects are called polarization. To overcome this problem, following modifications are done in the usual Wheatstone bridge method. The bridge is connected to the source of alternative current at a frequency of 550 to 5000 cycles per second is employed. Second, a headphone is used in the place of galvanometer because with alternating current, ordinary galvanometer fails to detect the null point. The third, the cell is placed in thermoset to keep the temperature constant. This is to avoid change in conductance with temperature. Fourth is electrodes are coated with platinum black. So resistance is of X is equals to resistance of R into length H. The resistance of electrolyte solution is converted to conductance using the following relation. C is equals to 1 by R. Now second is calculation of specific conductance. Specific conductance K of the electrolyte solution can be calculated as K is equals to C into L by A, where C is the conductance of the solution, L is the distance of separation of two electrodes and A is the area of cross section of electrodes. The quantity L by A is called cell constant. The cell constant is expressed in the unit centimeter inverse. The equation 1 can be written as specific conductance K is equals to conductance into cell constant. Once the specific conductance is determined, the equivalent conductance lambda EQ and the molar conductance lambda M of the solution can be determined. Third is determination of the cell constant. The cell constant L by A can be determined by measuring the distance L between the electrodes of the cell and their area of cross section. Actual measurement of these dimensions for a given cell is difficult. Therefore, an indirect method is used to determine the value of cell constant of a cell. The cell constant is generally not calculated from the values of L and A because these are difficult to measure for a cell. However, it is usually determined accurately by measuring the conductance of standard solution of KCl whose conductivity is known at different concentration and different temperature. Once the cell constant is known, the specific conductivity of a solution can be calculated from the observed conductance of the solution. Fourth is calculation of equivalent conductance. Equivalent conductance and specific conductance are related as lambda EQ is equals to K into 1000 by normality. The specific conductance and normality of the solution, we calculate equivalent conductance of the solution. Molar conductance of, now we will calculate molar conductance. Lambda M is equals to K into 1000 by molarity. Now sixth point is conductivity water. For accurate conductance measurements, the solutions are prepared in extra pure water which is free from dissolved impurities. The extra pure water has very small conductance. Such extra pure water is called conductivity water. The specific conductivity of this water is as low as 4.3 into 10 to the power minus 8 Simon centimeter inverse. For practical purposes, conductivity of water can be prepared by distilling ordinary water containing a small quantity of potassium permanganate, only a few crystals, and sodium hydroxide 0.6 gram into liters, twice in a Pyrex glass distillation apparatus. Next is variation of conductance, specific conductance, equivalent and molar conductance with dilution. Generally, the electrolytic conductance decreases with increase in the concentration or increase with increase in dilution. This is because the conductance is due to the presence of ions in the solution. The greater the number of the ions, the greater is the conductance. With dilution, more ions are produced in solution, so conductance also increases on dilution. The specific conductance is the conductance of 1 centimeter cube of the solution. On dilution, the specific conductance decreases because the concentration of ions per centimeter cube decreases and therefore the specific conductivity decreases. On the other hand, the molar conductivity and equivalent conductivity increases on dilution. This is because the molar conductance and equivalent conductance are the product of specific conductance and the volume of the solution containing 1 mole or 1 gram equivalent of the electrolyte. On dilution, the specific conductance decreases, but the increase in volume is much more than decrease in specific conductance. As a result, molar conductance and equivalent conductance are increases with the dilution. Now next is variation of molar conductance with dilution for strong and weak electrolytes. The variation of molar conductance on dilution for strong and weak electrolytes can be studied by plotting lambda m values against under root c. The variation of lambda m with concentration is discussed below. First, for strong electrolytes, the molar conductance of strong electrolyte in dilute solution varies with concentration according to the Debye-Hückel-Onsager equation as follows. Lambda m is equals to lambda m at infinite minus b under root c, where lambda m is the molar conductance at concentration C and lambda m infinity is the molar conductance at infinite dilution, and it is called limiting molar conductance. Here B is the constant whose values depends upon the type of electrolyte, nature of solvent and on the temperature. It is found that for strong electrolytes, example KCl, the Debye-Hückel-Onsager equation holds good at low concentration. As a result, the variation of lambda m is linear at low concentration, but it does not remain linear for higher concentration. The curve for the strong electrolyte shows that there is a small increase in molar conductance with dilution. This is explained as follows. Strong electrolytes are completely dissociated at all concentration. Thus, the number of the current carrying species, that is the ions, remains constant on dilution. Hence, the increase in molar conductance is not due to the presence not due to the increase in number of ions. It is due to the fact that at higher concentration the interionic attraction, that is the force of attraction between the oppositely charged ions, are appreciable. This retards the motion of ions, therefore molar conductance falls with increase in concentration. On the other hand, with decrease in concentration, the ions are far apart and the force of attraction between them decreases, due to which molar conductance increases with dilution. As the solution becomes more and more dilute, the molar conductance increases till it reaches a maximum limiting value. The value is known as molar conductance at infinite dilution, and it is denoted by lambda m at infinite dilution. The value of lambda m at infinite dilution can be obtained by extrapolating the curve to a value of under root 3 is equals to 0. For weak electrolytes, the weak electrolytes are dissociated to a lesser extent as compared to a strong electrolytes. Hence, the molar conductance of weak electrolyte is much less than that of a strong electrolyte at the same concentration. Figure 7 shows that the molar conductance of acetic acid, which is a weak electrolyte, is lesser than that of a strong electrolyte, that is KCl, at the same concentration. The curve shows that for a weak electrolyte, there is a large increase in molar conductance with dilution, especially near infinite dilution. The increase in molar conductance with dilution is due to the increase in the number of ions. Thus, the increase in molar conductance with dilution in case of weak electrolyte is due to the increase in the degree of dissociation or ionization of electrolytes on dilution. However, there is no indication of limiting value of molar conductance at infinite dilution even when the concentration approaches 0. From figure 7, it is observed that the curve for a strong electrolyte becomes linear at low concentration, and hence it can be extrapolated at 0 concentration to obtain the value of molar conductance at infinite dilution. But for weak electrolyte, the limiting value of molar conductance for infinite dilution cannot be obtained by extrapolation. There is an indirect method for obtaining molar conductance at infinite dilution for weak electrolyte, which is based on the Collard's law, which we will discuss in the section second. In section second, we will discuss about the theories of electrolytic dissociation and Ostwald's dilution law. First is Arrhenius' theory of ionization. Arrhenius studies the conductance of aqueous solution at different electrolytes. He proposed that the conductance of solution was due to the presence of ion. Arrhenius put forward this theory in ionization in 1884. Arrhenius' theory of ionization is summarized as follows. First, an electrolyte, when dissolves in water, splits up into charged particles called ions. The positively charged particles are cations and the negatively charged particles are called anions. In the modern view, the theory assumes that the electrolytes are already ionized in solid state and these ions are held by electrostatic forces. When the electrolyte is dissolved in water, the electrolyte dissociates to form separate cations and anions. For this reason, this theory is called the theory of electrolytic dissociation. Second point, the charge carried by cations is equals to the charge carried by anions. As a result, the electrical solution is electrically neutral. Third point, the charged ions move through the solution towards the oppositely charged electrodes. The migration of ions causes the passes electric current through the electrolyte solution. This explains the conductance of electrolytes and the phenomena of electrolysis. Fourth is the electrolyte may not be completely ionized. The ratio of dissociated molecules to the total number of molecules is called degree of dissociation and it is defined as alpha. So, alpha is equals to number of moles dissociated divided by total number of molecules. Fifth point, the ions formed in the solution constantly reunite to form undissociated molecules. Thus, a state of equilibrium exists between the undissociated molecules and the ions formed by the dissociation of electrolytes. The equilibrium constant for this equilibrium is equals to K is equals to A positive into the concentration of B negative, where K is equals to dissociation constant. Sixth point, the degree of dissociation increases on dilution and becomes maximum at the infinite dilution. Seventh is, the electrical conductance of an electrolyte solution depends upon the number of ions present in the solution. So, Greater the dissociation, higher is the conductance. Thus, the degree of dissociation of an electrolyte determines whether it is a strong electrolyte or a weak electrolyte. Mineral acids like H2SO4, HCl, alkalines like NaOH, KOH, and salts NaCl, NaNO3, etc. have high conductance values because they are almost completely dissociated in the aqueous solution. These substances are termed as strong electrolytes, whereas organic acids, some organic inorganic acids like H2CO3, H3PO4, and bases like NH4OH, MgOH twice, etc. have poor conductance because they have low degree of dissociations, and such substances are termed as weak electrolytes. Next, factors affecting the degree of dissociation. First is nature of solute. Some electrolytes like inorganic acids, bases, and salts are almost completely ionized in aqueous solution. These are terms and strong electrolytes. Some substances like organic acids and bases dissociates only to small extent and are called weak electrolytes. Second is nature of the solvent. In solid electrolyte, the ions are held by strong electrostatic force of attraction. Every solvent has a definite value of dielectric constant, which is defined as its power to weaken these forces of attraction and cause the dissociation of the electrolyte. Solvents with high dielectric constant are highly ionizing, with those with low dielectric constant are poorly ionizing. For example, water has very high dielectric constant, which is equal to 80. These ionic compounds get quickly dissociated in water as compared to other solvents. Third point is concentration. The degree of dissociation of electrolyte increases as the concentration decreases. As the concentration approaches zero or dilution approached infinity, the degree of dissociation approaches unity. That means it is its limiting value. Fourth point is presence of common ion. The degree of dissociation of an electrolyte is suppressed in the presence of an electrolyte that furnishes a common ion. This effect is termed as common ion effect. For example, the dissociation of H2 decreases in the presence of HCl. Fifth is temperature. The degree of dissociation increases with rise in the temperature. Next is Ostwald dilution law, or we can also say ionization of weak electrolytes. It has been mentioned earlier that weak electrolytes are ionized only partially. According to Arrhenius' theory of ionization, the ions formed as a result of dissociation of weak electrolyte are present in dynamic equilibrium with the undissociated molecules. Consider the ionization of binary weak electrolytes, that is AB. AB is dissociated into A positive plus B negative. In 1988, Ostwald applied law of chemical equilibrium to such chemical equilibria and obtained a relationship called Ostwald dilution law. Let 3 moles per liter will be the concentration of the electrolyte in the solution, and alpha is the degree of the dissociation. The concentration of the various species at equilibrium would be under. AB aqueous is dissociated into A aqueous plus B negative aqueous. At initial concentration, AB is C and A positive and B negative are 0. At equilibrium, A positive will be C alpha and B positive will be C alpha. So, AB will become C into 1 minus alpha. Now we have applying law of chemically equilibrium, and we will get Kd is equals to C alpha square divided by 1 minus alpha, where Kd is dissociation constant of the electrolyte AB. Like any other equilibrium constant, Kd is a constant only at constant temperature. For weak electrolytes, at ordinary concentration, alpha is greater than 1, less than 1. Therefore, alpha can be neglected in comparison to 1 in the denominator of expression 1. Then the simplified formula becomes Kd is equals to C alpha square. Alpha square is equals to Kd divided by C, and we will get alpha is equals to Kd divided by C under the root. Expression 1 and 2 are the forms of Ostwald dilution law. Expression 2 can be expressed at degree of dissociation is inversely proportional to the concentration. From equation 2, it is obvious that the degree of dissociation alpha increases as concentration decreases. As C approaches 0, alpha approaches 1. This Ostwald dilution law may be stated as for a weak binary electrolytes, the degree of dissociation is inversely proportional to the square root of the molar concentration. For a weak binary electrolyte, the degree of dissociation is directly proportional to the square root of the volume in liters containing 1 mole of the electrolyte. Now, here is the validity of Ostwald dilution law. The test the reliability of Ostwald dilution law, the degree of dissociation alpha is determined from conductance measurement at various concentrations for different electrolytes. The value of alpha are obtained experimentally using the following expressions. Lambda is equals to lambda c divided by lambda at infinite. Lambda c and lambda are the equivalent conductivity at concentration c and infinite dilution respectively. These values are determined from conductance experiment using Collard's law. The values of alpha then substituted in expression Kd is equals to alpha square divided by 1 minus alpha into V. If the values of K are found to be constant, the Ostwald law is verified. Now here are some limitations of Ostwald dilution's law. First is Ostwald dilution law holds only for weak electrolytes in dilute solutions and fails completely in case of strong electrolytes like HCl, NaOH and salts, etc. Second, Ostwald law is based on Arrhenius theory of dissociation, according to which only a fraction of electrolyte dissociated at ordinary concentrations and a complete fraction of electrolyte dissociates at ordinary concentration and a complete dissociation occurs only at infinite dilution. This is true only for weak electrolytes as strong electrolytes are almost completely dissociated at all concentration. Hence the formula lambda c divided by lambda at infinite does not give correct value of alpha. The derivation of L of Ostwald law is based on the law of mass action, which is not applicable to the ionic equilibrium where the concentration of ions is high. Thus, the law of mass action in its simple form does not hold for the equilibria involving strong electrolytes. As a result, the correct value of alpha is not obtained. Hence, Ostwald law is not obeyed in case of strong electrolytes. Explanation for failures of Ostwald dilution law. First is strong electrolytes are almost completely dissociated at all concentration. That means alpha is equals to 1. Second, the ratio lambda c divided by lambda infinite at infinite does not represent the degree of dissociation alpha of strong electrolyte but is only a conductivity ratio. For example, alpha is equals to lambda c by lambda naught does not hold because alpha is equals to 1 for strong electrolyte. Lambda c is not equal to lambda c divided by lambda infinite. In case of strong electrolyte, the increase in lambda c with dilution is not due to the increase in the degree of dissociation, but due to the increase in the mobilities of the ions of strong electrolyte. Fourth is the lower value of lambda c as compared to the value of lambda at infinite is due to the decrease in the mobility of the ions arising from relaxation and electrophoretic effects. However, at infinite dilution, these two retarding effects disappear, hence the value of lambda c becomes maximum at infinite dilution that is. The results obtained from weak electrolyte namely acetic acid and for strong electrolytes namely KCl. It is clear for acetic acid that the value of Kd remains constant for all dilute solution where the KCl the value of Kd falls rapidly with the dilution. Now applications of Ostwald dilution law. Ostwald dilution law is applicable only to weak electrolytes. It is used to calculate dissociation constant of weak acids and weak bases by determining the degree of dissociation alpha from conductance measurement at given concentration C. Using the calculated value of Kd for weak acids and weak bases which is constant at particular temperature, the degree of dissociation of that weak electrolyte can be determined at any concentration. Now, here are some also the limitations of Arrhenius theory. First is, according to Arrhenius theory, ionization of electrolytes takes place in aqueous solution. However, Bragg in 1912 through X-ray diffraction study showed that many electrolytes are ionized even in the crystalline state that is NaCl. Strong electrolytes conduct electricity. Second is strong electrolyte conduct electricity even in molten state. So the ionization of electrolyte takes place even in the absence of water. Thus, Arrhenius theory could not explain the role of water in the dissociation of the electrolyte. Third point is Ostwald dilution law, which is based on Arrhenius theory, fails for strong electrolyte. The values of equilibrium constant for dissociation of strong electrolyte were found to vary with the concentration of electrolyte, that is a constant value of dissociation Kd is not valid. Fourth is there is a good agreement between the degree of ionization calculated from the conductivity measurement, and the one calculated from measurement of colligative property only for univalent electrolytes like NaCl, etc. But marked disagreement in the values of lambda was found for bivalent electrolytes such as CuSO4, HgSO4, etc. Fifth point is Arrhenius theory proposes that equivalent conductance of electrolytes increases with dilution. This increase in case of weak electrolyte is because on dilution more of the unionized molecules of weak electrolyte dissociates. In case of strong electrolyte like NaCl, which are fully dissociated even in solid state, the increase of equivalent conductance with dilution could not be explained. The increase of equivalent conductance with dilution must be due to some interionic forces of attraction between the ions which have not been taken into account by Arrhenius theory. Sixth point, it could not explain the variation of transport number with the concentration. Next is Debye-Huckel theory of strong electrolytes. In case of weak electrolytes, the increase in equivalent conductance with dilution can be easily explained as on the basis of Arrhenius theory, according to which the conductance increases due to increase in dissociation of weak electrolytes with the dilution. But this explanation cannot be applied to strong electrolytes as they are almost dissociated even at the moderate concentration. In fact, the conductance of an electrolyte solution depends upon two factors. First is number of the ions in the solution. Second, speed of ion or the ionic mobility. In case of weak electrolyte, the increase in conductance on dilution is attributed to increase in the number of ions due to increase in the dissociation of the electrolytes. The speed of ions are not affected on dilution because the number of ions formed in case of weak electrolyte is very small, and hence these ions move independent of each other without any interference in their mobility from the surrounding ions. But in case of strong electrolytes, the number of ions formed is very large. As a result, the mobility of ions is hindered by the surrounding ions. On dilution, the hindrance due to neighboring ion decreases. The inter the intermobility increases, and there is an increase in the equivalent conductance of strong electrolytes. And quantitative explanation of the behavior of dilute solution of strong electrolytes was put forth by Debye and Huckel in 1923. Their theory is based on the idea that at high concentration the ions are close together. Because of electrical attraction among the oppositely charged ions, each ion in solution is surrounded by a large number of oppositely charged ions, which constitute an ionic atmosphere of opposite charge and hence affect the speed of the ion. The electrostatic force attraction among the oppositely charged ions, which affect the speed of the ion in electric field, are known as interionic effects. The two types of interionic effects are described as follows. First is asymmetry or relaxation effect. Considered a central positive ion, this is surrounded by ionic atmosphere of negatively charged ions. The ionic atmosphere is symmetrical in absence of electrical field. When an electric field is applied, the positive ions move towards cathode and negative ions atmosphere moves towards the anode. This leaves a large number of negative ions behind that in front of positive ions, and then the symmetry of the atmosphere about the central positive ion is destroyed. The excess negative ions left behind drag the positive ion backwards, and this slows down its motion in the forward direction. This effect arises due to asymmetry of the ionic atmosphere of ions, and hence it is known as asymmetry effect. It can be explained in any other way by considering that the positive ion which leaves the ionic atmosphere of negative ions behind has to rebuild a new ionic atmosphere around it. However, the process of building up and dying away of ionic atmosphere is not instantaneous. The formation of new ionic atmosphere does not take place at the same rate at which the old ionic atmosphere dies out. Each of these processes takes some time, which is called as time of relaxation. During the time of relaxation, the old ionic atmosphere drags the moving ion backward and thus retards the motion of the ion. For this reason, asymmetry effect is also known as relaxation effect. Moreover, the central ion moves into an atmosphere where there is an excess of ions of its own charge, and this is and this also has the retarding effect on the moment of ions. Second is electrophoretic effect. In solutions, the ion present in the solvated form. Each ion in the ionic atmosphere is associated with some molecules of the solvent. Under the influence of electric field, the central ion moves in one direction and it is oppositely charged in charged ionic atmosphere along with the associated solvent molecules move in the opposite direction. Thus, the ionic atmosphere with its solvents molecule causes a retarding effect on the moment of the central ion. This retarding effect is called electrophoretic effect. Besides these two effects, another retarding force is the frictional resistance offered by the medium due to the viscosity of the solvent and the dielectric constant of the solvent. This frictional resistance increases with increase in the viscosity and in the dielectric constant. Thus, the ionic atmosphere with its solvent molecule causes a retarding effect on the moment of the central ion. This retarding effect is called electrophoretic effect. Both the factor that is asymmetric effect and electrophoretic effects are present in the solution of strong electrolyte and reduce the velocity of the ion and solution. Hence, the value of equivalent conductance is lower than the value at infinite dilution. Our next topic is Debye-Heckel-Onsager equation for the strong electrolyte. Taking into account these retarding effects, Debye and Heckel in 1923 derived an equation to show that the variation of electric equivalent conductance with concentration. Later on, Sager further extended the theory and derived an equation known as Debye-Heckel-Onsager equation or simply Onsager equation. For univalent electrolytes, the equation is written in the form lambda C is equals to lambda infinite dilution minus 82.4 divided by n dt half plus 8.20 into 10 ki power 5 divided by dt ki power 3 by 2 lambda naught bracket close into concentration at C. Lambda is equivalent conductance of electrolyte at concentration C. Lambda naught equivalent conductance of electrolyte at infinite dilution. D is dielectric constant of the solution solvent. Eta is equals to coefficient of the viscosity of the solvent. T is equals to the temperature. C is equals to the concentration of the solution. Since the dielectric constant D and the coefficient of viscosity eta are constant for a particular solvent, thus at constant temperature, the equation 1 becomes lambda C is equals to lambda naught minus A plus B lambda naught into C, where A and B are the constant for a given solvent and in temperature. The constant A and B involved under root dt in the denominator. Thus, when D and dt increases, D and T increases, the interionic attraction would decrease. Thus, decrease in equivalent conductance will be less when dielectric constant or temperature is high. The first term A root C is the measure of degree of equivalent conductance due to the electrophoretic effect. The constant A in this term involves eta, the viscosity of the solvent in the denominator, showing that in a more viscous solution solvent, the decrease in equivalent conductance will be less because the speed of both the ions and the ionic atmosphere is slowed down in a more viscous solvent. The second term b lambda at infinite dilution under root c in the equation gives the decrease of equivalent conductance due to symmetrical effect. Now, what is the significance of Debye-Heckel theory? This theory has been used to explain the conductance behavior of strong electrolyte. Debye-Heckel theory successfully explains why the equivalent conductance of strong electrolyte at any concentration lambda C is less than the limiting value of conductance at infinite dilution. In spite of this fact that strong electrolytes are completely ionized, we know that electrolyte dissociates in solutions to produce cations and the anions. Now we will do section third. In section third we will do the migration of the ions and the transference number, or we can also say it transport number. Now next is migration of the ions. NaCl in aqueous solution dissociated into Na positive, Cl negative. CuSO4 is dissociated into Cu positive, Cu2 positive plus SO4 2 negative. When the current is passed the solution of an electrolyte, the ions migrate to the opposite electrodes. Thus, in the solution of AgNO3, the cations Ag positive ions moves towards the cathode, while the anions NO3 negative ions moves towards the anode. The movement of ions towards a positively charged electrodes is called the migration of ions. The migration of ions through the electrolyte solution can be demonstrated by the following experiment. Take a U-shaped tube made of hard glass. The lower part of, a, of the tube U is filled with the 5% of aqueous solution of agar-agar and a small amount of copper dichromate. Since the salt is not available as such, it is obtained by mixing equimolar proportions of copper sulfate and potassium dichromate. It is green in color and it is allowed to set into jelly in agar-agar on cooling. The surface of the green gel is marked by placing a small amount of powdered charcoal. Over the charcoal layer in both the limbs, a layer of KNO3 solution in agar-agar is placed. This layer also sets into jelly on cooling. Finally, an aqueous solution of KNO3 is added into a lens and potassium electrodes are inserted in it. When electric current is passed, the copper to positive ions moves towards the negatively charged electrode and their migration is indicated by the rise of blue color into jelly under this electrode. The orange colored Cr2O7 negative ions moves up towards anode in the other arm of the tube. By comparing the movement of these colored bands in two limbs, the velocities of two ions can be compared. Next is velocity of ions and the amounts liberated at electrodes, normally we or normally we can say it Hitov theoretical divides. In accordance with Faraday's second law of electrolytes, which states that when same quantity of electricity is passed through solutions of different electrolytes, the ions are always liberated in equivalent amounts. But the speed of cations moving towards cathode and the anions moving towards the anode are not necessarily the same. After experimental studies, Hitov made following observation. The speed of the cations moving away from anode is directly proportional to the fall of the concentration of cations around the anode. And the speed of an anion moving away from a cathode is directly proportional to the fall in the concentration of anions around the cathode. However, Hittorf gave a general rule known as Hittorf rule, which is stated as the fall in concentration around any electrode is directly proportional to the speed of the ion moving from it. Hittorf rule is illustrated by Hittorf theoretical device. Considered a cell containing an electrolyte solution. It is provided with an anode A and a cathode C. Dotted lines AA and BB are the imaginary planes which divide the cell into three compartments. First plus signs represent a cation while negative sign represent an anion. Before electrolysis, let there be 13 pair of ions in the cell. The number of ion pairs in the middle compartment is 5 while there are 4 ion pairs in the two other compartments. Now the following different cases may be considered. The condition of the system at the beginning of electrolysis is shown as in the figure 11 as 1. So, case 1 when only anions move. Suppose that only anions are able to move under the influence of applied potential. When two ions move from cathodic department and enter into anodic department, that means situation second is obtained. Although cations have not moved at all yet, the number of discharged anions and cations are the same. That means 2. It seems that the concentration in anodic department has not charged while the cathodic department in the concentration has fallen by the two molecules. Case second, when the cations and anions move at the same rate. When two cations move to the cathodic department and two anions move to the anodic department, we get the situation third. In this case, the number of ions liberated at each electrode is the same, that is 4. The concentration of the cathodic department and the anodic department has fallen to the same extent, that is by 2 molecules. Case third, when the cations move at twice the speed of the anions. In this case, let two cations move to the cathodic department as the speed of anions is half the speed of cations, therefore only one anion enters the anodic department. This is shown in condition 4. The number of ions discharged at each electrode is the same, that is 3. The concentration in the cathodic department has fallen by 1 molecule, whereas the concentration in anionic department has decreased by 2 molecules. From above discussion, the following results are obtained. The ions are always discharged in equivalent amounts on the oppositely electrodes, irrespective of the speed of the ions. Second is loss in concentration around any electrode is proportional to the speed of the ions moving away from it. This is heteroflow. We know that fall in concentration around anode divided by fall in concentration around cathode is equals to the speed of the cation divided by speed of the anion. Speed of the cation is represented by U positive and the speed of anion is represented by U negative. In writing the above expression, it is assumed that the liberated ions do not react with the material of the electrodes. In many cases, the discharged ions react with the electrodes, causing an increase in concentration around the electrode rather than the fall in the concentration. On one such cases is discussed ahead, when the electrodes are attacked by discharged ions. Let us let us consider the electrolysis in a silver voltmeter. A silver voltmeter contains silver electrodes placed in silver nitrate solution. On passing electric current, we observe that instead of a fall in concentration of AgNO3 around the anode, there is an increase in concentration in anodic department. The three conditions in silver voltmeter are shown in figure 12. We find that in every case there is an increase in concentration in anodic department. This is due to the fact that each nitrate in NO3 negative that reaches the silver anode react with Ag positive ions to form AgNO3. The increase in concentration in anodic compartment takes place even when Ag positive negative ions moves from anodic to cathodic department as shown in the figure. The increase in concentration around the ions if no Ag positive ions had migrated towards cathode can be determined by placing a silver coulometer or copper coulometer in the circuit. Let X be the number of gram equivalents of copper or silver deposit in the coulometer. The gram equivalence is the total increase in the concentration around the anode if no silver ions are migrated towards the cathode. However, the actual increase in concentration is less due to the migration of Ag positive ions from the anode. Let Y gram equivalents be the actual increase in the concentration of Ag positive ions in N compartment, then fall in the concentration in the anodic compartment due to the migration of Ag positive ions is equals to X minus Y gram equivalent. Fall in concentration in cathodic department is equals to increase in concentration in anodic compartment is equals to Y gram equivalent. The ratio of speed of ions is given as speed of Ag positive divided by speed of Ag negative. So speed of NO3 negative is equals to X minus Y divided by Y. Now next is transference number or transport number. During the passage of electric current through an electrolyte, the ions migrate towards electrodes. Thus, the current is carried by anions and the cations. The current carried by an ion is directly proportional to the speed of the ion. The higher the speed of the ion, the more is the current it carries and greater is its transport number. The fraction of total current carried by an ion is called its transport number, transference number or Hittorf number. If UC represents the speed of the cation and UA represents the speed of the anion, then the current carried by the cation is directly proportional to UA, that is equals to KUA. Similarly, the current carried by the anion is directly proportional to UA, that is KUA. Total amount of current carried is equals to KUC plus KUA, and we will now K is a constant. Now we will हम इसको बाहर निकालेंगे, then we will get UC plus UA. Transport number of cation NC is equals to KUC divided by K bracket UC plus UA into UA. Then TC is equals to UC divided by UC plus UA. The transport number of anions similarly we can calculate. By adding, now we will note that Tc plus Ta is equals to 1. That is the sum of transport number of cations and anions of an electrolyte is always unity. Hence, whole of the current is carried by the anions. Now we will do the determination of the transport number. Here are two methods for the determination of transport of an ion. First is hit-off method and second is moving boundary method. Now first we will do hit-off method. Principle of this method is based on Hittorf rule. According to this rule, the fall in the concentration around any electrode is proportional to the speed on the ion moving away from it. Fall in concentration around cathode is divided by fall in concentration around anode is equals to UA plus. You see, now we will add 1 on the both side and we will get fall in concentration around cathode plus fall in concentration around anode divided by fall in concentration around anode is equals to UA plus UC. Now we will inverting this in both sides and now we will get fall in concentration around anode is divided by total fall in concentration around both electrodes is equals to Tc. Tc is here the transport number. The number of gram equivalents lost from both of the electrodes is equal to the number of gram equivalents deposited or discharged at electrodes. This can be measured by placing a silver or copper collimator in series. According to Faraday's second law, when the same quantity of electricity flows through the silver or copper collimator, the same number of gram equivalents of Eg or Cu will be deposited then. Tc is equals to number of gram equivalent lost from anodic department divided by the number of gram equivalent deposited in the collimator. Knowing the value of Tc, the value of Ta can be found as Ta is equals to 1 minus Tc. From this equation, we can calculate transport number and hence their relative ionic mobilities from measurement of fall in the concentration during electrolysis. It should be noted that above calculations are applicable only when the electrodes are not attackable. Now we will do measurement of transport number by Hitov method. For the measurement of transport number, the apparatus should be used such that there should be three separate compartments: anodic, cathodic, and a middle compartment. Second, during electrolysis, there should be no intermixing of the solution of this compartment. Third, the solutions from any compartment can be withdrawn without disturbing the solutions in any other compartments. This is achieved by using a suitable apparatus in which the anode and cathode compartments are separated by middle compartment. It consists of two vertical glass tubes joined together through a U-tube in the middle. All the three glasses, all the three tubes are provided with stopcocks at the bottom. By closing these stopcocks, the mixing of the solution in the cathode and anode limbs can be stopped. The cathode and anode is made up of platinum, which is non-attackable electrodes. The cathode and anode may be made up of Ag or copper if the transport number of Ag positive or copper negative ions to be determined. A silver or copper voltmeter is placed in the series with the solution so that same quantity of electric current is passed through them. Procedure: the apparatus is filled with the electrolyte solution of the ions where transport number is to be determined. Second, the electrodes are inserted and the cell is connected in series with a silver or a copper collimator. The concentration of the electrolyte is found by titrating the solution with the suitable reagent. Fourth, a steady current of 0.01 to 0.02 ampere is passed for 2 to 3 hours so as to produce appreciable amount of the current. After electrolytes, the stopcocks of U-tips are closed. The whole liquid in the anodic compartment is carefully drained into a weight flask and its weight is determined. It is titrated to determine the weight of the electrolyte present. Seventh point is the weight of the silver deposited in silver collimator is determined. Eighth is there should be no change in the concentration of the solution in U2 and U2. The solution from the central department is taken out and titrated to know that if there is any change in the concentration of the electrolyte. In case of concentration change in electrolyte, the experiment is related. If the above experiment is performing using silver electrodes, in this case nitrate ions attack the silver anode. Consequently, there is an increase in concentration of Ag positive ions rather than decrease. The same experiment can be performed by using platinum electrodes to avoid the attack of the ions on the anode. Now the factor affecting transport number. We know that the transport number of an ion is directly proportional to the speed of the ion. The speed of the ion in turn depends upon various factors which are discussed below. First, nature of the ion. In general, the smaller the size of the ion, greater will be its speed. Hence, the transport number of smaller ions will be higher. That is the example. The transport number of H positive ion is greater than that of Na positive or K positive ions. Second, nature of other ions present in the solution. It may be pointed out that the transport number of an ion does not depend upon the mobility of ion alone. It also depends upon the mobility of other ion which it is associated. For example, the transport number of Cl is found to be less in HCl than in NCl. This is due to the fact that the size of H positive ions are much smaller than N positive ions. Therefore, the speed of H positive ions is much greater than the speed of the N positive ions. Therefore, the denominator term in equation 1 is bigger than equation 2. Thus, the transport number of Cl negative in HCl is less than that of HCl. Third is degree of hydration of ions. We know that the ions in solution are hydrated. Smaller ions have strong electrostatic fields and are heavily hydrated, and the large ions, because of the weaker electrostatic fields around them, are less hydrated. The speed of an ion is largely affected by the extent of hydration of the ion. As a result, the transport number of the ion is also affected. For example, lithium positive ions is smaller in size than N positive ions, and it is expected to have larger speed and thus higher transport number than that of N positive. But actually it is reserved. The transport number of N positive is higher than that of lithium positive ion. This is because the smaller N positive ion is much more hydrated from than Na positive ion. Similarly, the transport number of K ion is greater than that of Na positive ions because of more hydration of Na positive ions as compared to the hydration of K positive ions. Fourth factor is temperature. It is observed that the ions tends to reach a transport number 0.5 as the temperature is increased. If the transport number of an ion is greater than 0.5, there is a decrease in transport number as the temperature is raised. While in case of ions having transport number less than 0.5, there is an increase in the transport number with increase in the temperature. For the ions having transport number around 0.5, there is a very small change in transport number with an increase in temperature. It is thus clear that in general the transport number of ions tends to approach 0.5 as the temperature is raised, if the ions tends to attain equal speeds at high temperatures. Fifth is concentration. It is observed that the change in the transport number of an ion with change in concentration is very small. But in some cases, the increase in concentration results in the formation of a complex. In such cases, there is notable change in the transport number. For example, when the concentration of cadmium iodide solution is increased from 0.005 m molarity to 0.25, the transport number of cadmium to positive ions falls from 0.444 to 0.003. At higher concentration, the transport number becomes 0 and even attains a negative value. Sixth is intra-ionic effects. The ionic mobility and hence the transport number are greatly affected by intra-ionic effects, namely relaxation type and electrophoretic effects. Now, our last section of this chapter is Collard's law, or we can also saw the law of independent migration of ions, its application its application to conductance measurement. First is Collard's law. Collards studied the molar conductance at infinite dilution for strong electrolytes. He found an interesting pattern between the values of molar conductance infinite dilution for strong electrolytes. It was observed that the difference of molar conductance infinite dilution of different pairs of strong electrolyte having a common cation or anion value was the almost same. It is observed that the difference between the molar conductance of K positive and Na positive is 23.4 ohm inverse centimeter square mole inverse, irrespective of the anion. Similarly, the difference between the molar conductivities of chlorine negative and nitrate ion is 4.9 ohm inverse centimeter square mole inverse, irrespective of the cation associated with them. Thus, it may be concluded that each of the ions make a definite contribution to the molar conductivity at infinite dilution, irrespective of the other ions. The individual contribution of the ions towards that molar conductivity of electrolyte is called the molar ionic conductivity. As a result of these observations, Collard's gave a generalization called the Collard's law. It states that at infinite dilution, where the dissociation of electrolyte is complete, the molar conductivity of an electrolyte is the sum of the limiting ionic conductivities of the cations and anions, each multiplied to the number of ions composing one formula unit of the electrolytes. Collard's law for an electrolyte AXBY mathematically stated as molar conductance at infinite dilution of AXBY is equals to X times of molar conductance at infinite dilution of A positive plus Y times of molar conductance of B negative at infinite dilution, where X and Y represent the number of positive anions furnished by one formula. Unit of electrolyte molar conductance infinite dilution AXBY is the limiting molar conductance of the electrolyte AXBY, and lambda naught A positive and lambda naught B negative are the limiting molar conductivities of the cation A positive and the anions B positive respectively. Illustration. Based on Collard's law, it is possible to calculate the molar conductivity of weak electrolyte at infinite dilution by simply adding and subtracting the values at infinite dilution of given electrolytes. For example, for acetic acid we can calculate molar conductance infinite dilution of sodium acetate plus in molar conductance of infinite dilution of HCl minus molar conductance of infinite dilution of NaCl. From this we can calculate the molar conductance of acetic acid at infinite dilution. The equivalent conductance of an electrolyte at infinite dilution is equal to the sum of the equivalent conductance of cations and anions. This is accordance with Collard's law. The equivalent conductance del lambda EQ and molar conductance are related as EQ is equals to lambda m divided by x z positive, where n x and y are the number of cations and anions respectively present in var formula unit of the electrolyte, and z positive and z negative are the charges on the cations and anions respectively. Collard's law is called the law of independent migration of ions because at infinite dilution all the electrolytes are completely dissociated and all intrionic effects disappear. In such conditions, each ion migrates to the electrolytes are completely dissociated and all intra-ionic effects disappear. In such conditions, each ion migrates to the electrode independent of the nature of the co-ion and makes a definite contribution towards the molar conductivity of the electrolyte, which depends only on its own nature, not at all the ion with which it is associated. Next is ionic mobility. The ionic mobility of an ion is the speed of an ion in the electrical field of the unit strength. It may be defined as a distance traveled by an ion per unit time when a potential gradient of 1 volt per unit distance is applied. It is represented by mu, and it is equal to the speed of the ion divided by potential gradient applied. And the units of this is meter square per second per volt. Now next is effect of temperature and pressure on the molar conductance. The molar conductance is found to increase with increase in the temperature. From equation 6, it is clear that the molar ionic conductance is inversely proportional to the coefficient of viscosity eta of the solvent. The viscosity of the solvent decreases with increase in temperature. The smaller ionic conductance of an ion, lambda positive or negative, increases as the temperature increases. For example, four ions other than H positive and OH negative, the increase in ionic conductance is about 2% for 1 degree, whereas in the temperature range of 0 to 100 degrees Celsius. Whereas for H positive and OH negative, the increase in ionic conductance is about 14 to 16% respectively per degree rise in temperature. Molar ionic conductance decreases on increasing pressure. This is because the viscosity of the medium increases on increase of pressure. Now, here are some applications of Collard's law. The conductance measurement have many applications in theoretical as well as analytical chemistry. Some of the applications are discussed as follows. First is degree of dissociation of weak electrolyte. Arrhenius theory assumes that in case of weak electrolytes, the increase in equivalent conductance on dilution is due to the increase in the degree of dissociation of the electrolyte. It is evident that when limiting values of equivalent conductance is approached, the degree of dissociation is unity. Thus, the degree of dissociation lambda is given by lambda is equals to lambda c divided by lambda naught, where lambda c is the equivalent conductance at any concentration, and lambda naught is the equivalent conductance at infinite dilution. It may be noted that above relationship holds only for weak electrolytes. The value of lambda naught for strong electrolytes can be calculated by using the Collard's law. Second is Dissociation constant Ka for of weak acids. Consider the dissociation constant of acid Ha having initial concentration as C moles per liter. Let alpha be the degree of dissociation. Then at initial concentration Ha is equals to C, and the H positive ions and the A positive A negative ions concentration are 0, and when an equivalent concentration H positive, the concentration of H positive is C lambda and also H negative is C lambda, and the concentration of H is equals to C into 1 minus lambda. Applying the law of chemical equilibrium, the dissociation constant of a weak acid can be written as Kd is equals to C lambda square into 1 minus lambda. Next is solubility of sparkingly soluble salts. Salts such as AgCl, PbSO4, BSO4, etc. dissolves to a very small extent in water and therefore are called sparingly soluble salts. Since they are very high, very slightly soluble, their solutions may be spoken taken as infinite dilution. Moreover, because their solutions are saturated, their concentration may be taken equal to their solubility. Thus, by determining the specific conductivity and equivalent conductance of such solution, we can easily calculate the solubility as with the solubility of sparkingly soluble solution soluble salt in g gram equivalents per liter. Then the volume of the solution in centimeter cube containing 1 gram equivalent of the salt will be 1000 divided by equivalent conductivity and specific conductance K of such solutions are related as lambda is equals to K into 1000 into S. As the salt is sparkingly soluble, its solution may be taken as infinite dilution. So, lambda may be taken as equals to at infinite. Thus, we can write lambda at infinite dilution is equals to K into 1000 into S. S is equals to K into 1000 into lambda at infinite dilution. A lambda can be calculated by applying the Collard's law. To calculate solubility in gram per liter, the quantity S is multiplied with equivalent mass of the. Last application of this is determination of solubility product of a sparkingly soluble salt. Let us consider the general case of sparkingly soluble salt, say AB. When the salt is dissolved in water, to get a saturated solution at a particular temperature, there exists an equilibrium between the undissolved solid salt and the ions A positive aqueous and B negative aqueous in solution. This can be expressed as AB solid. When it is dissolved in water, it is dissociated into A positive and B negative. When we will write Kc is equals to A positive concentration multiplied with B positive concentration divided by AB. Since the molar concentration of solid is taken to be constant, say K, we may write this equilibrium. Kc is equals to Kc into K is equals to a concentration of A positive into concentration of B positive. Or we can also write is Ksp is equals to concentration of A positive into concentration of B negative, where Kc into K is equals to Ksp is known as solubility product and is equal to the product of the ionic concentration for constant solutions. For any sparkingly soluble salts AXBY which dissociates to set up the equilibrium, AXBY will dissociate into x into a raised to power y positive plus b y into b raised to power x negative. If S represents the concentration or solubility of sparkling salts AXBY, then from the above equilibrium we can write A concentration of A raised to power y positive is equals to x into S into, and the concentration of B raised to power x negative is equals to y into S. Then we will get Ksp is equals to x into s की power x and concentration of y into s की power y. For calcium phosphate Ca3PO4 2 x is equals to 3 y is equals to 2, and now we will calculate the Ksp for this solution. Now solubility S of the sparkling salt can be determined by conductivity measurements as explained in application number 3. The solubility product of salt can be easily evaluated provided by the solution. So that's all about the chapter electrochemistry, and thank you and have a cheerful